So in this video we're going to be covering the basics of digital metering. So we're going to cover various different digital meters here, including dBFS, dBFS RMS, LKFS and LUFS, and True Peak meters. And along the way we're going to cover some theory that helps you understand these better, including the difference between dBFS and old school analog meters. We're going to cover the equal loudness contours, we're going to cover K weighting, and we're going to cover LUFS timing references. So let's jump in with the granddad of digital metering, which are dBFS. So dBFS stands for decibels full scale, and most of you will be familiar with decibels as a kind of reference for audio signal strength. And this effectively is a logarithmic scale, and this means that the range that our auditory system can handle is very broad, and representing these in a linear way would end up with figures that are very difficult for us to comprehend and calculate, whereas representing them as decibels in a logarithmic scale means that they're more manageable for us, and it's actually more closely aligned to how we're actually hearing in the first place. Now, FS stands for full scale, and this means that it's representing the full scale of our hearing, and its reference point of 0 is actually the maximum permitted level of a system, or the clipping point. So this means if you hit 0, you can't actually get any louder than that, and if you try and turn the level up further than that, you're actually going to end up with hard clipping and distortion. Okay, and with digital, it's very important that you avoid this point. Okay, and having a reference point of this maximum level is actually very, very convenient. Okay, so usually you'll see that you want to steer well clear of 0. Okay, and actually all values are negative on a dBFS scale apart from 0 itself. So for instance, minus 14 dBFS is 14 decibels from the maximum permitted level, and all levels on a dBFS meter are peak, so every single sample will have its own reading. Okay, so this is really, really appropriate, because remember, we want to avoid this clipping point and we want to make sure we have plenty of headroom. And if the meter is only averaging out the signal level, we're not going to know if a certain portion of that signal has actually clipped. Okay, so we want to make sure that not only are we avoiding 0, but we also need to know that no part of our signal has exceeded 0 either. So dBFS is a peak reading, okay, and the maximum level is 0. So we're always going to be working with negative values. So let's go into Pro Tools, and I'm just going to show you these peak readings. Okay, so we've got Pro Tools open here, and we can see that we're set to Pro Tools Classic. Now this is a standard peak reading. Okay, so let's go ahead and play a bit of this track. I'm going to leave it muted just so that I can talk over it, and I just want you to look at the level on the meter. We can see that we're at 0 here and it doesn't go any higher. Okay, so what you can see there is the bar graph kind of bouncing up and down, and there are no other indications, okay, other than this solid bar and it showing a kind of amber looking peak indicator here, and this is showing you during a certain section the loudest point that it's got to. And if we look down at the bottom here, we've got 2 other kind of numerical readings. Now this first one on the left is showing you the level of the fader, so this is at minus 5.7, but the one on the right is showing you the kind of maximum peak level during the portion you just played. And if I left click on this, okay, it will reset. Okay, that's great. So this is showing you the dBFS reading. It's showing you the instantaneous peak levels. Okay, so now let's compare digital working levels and analog working levels. And to understand why the two needed different types of meters, we need to understand how an analog system works a little bit better. And with a digital system, as you reach that point of no return, it suddenly started to hard clip, i.e. just truncate and just disregard everything over a certain level. Whereas in the analog domain, as you reached its point where it started to not be able to handle that amount of information, it would soft clip, meaning that it would kind of round off. And as you drove that harder and harder beyond that point of no return, it would start to hard clip. So you had this region where technically you were clipping it a little bit, but it actually sounded nice to our ears. And therefore, with analog meters, we didn't used to be so worried about its absolute peak level. We just used to use our ears to find that kind of best balance and that appropriate point where we weren't getting too much distortion, but it sounded good. And in old school analog recording mediums, you also had the problem that if you recorded too low, you would end up with a lot of hiss and noise, because these old tape machines and other mechanical devices actually had quite a high noise floor. So in the analog world, what you used to do is set a reference point around the optimal level to record at. So here we see two types of old school analog meter. We've got the oldest here on the right, the VU meter, which stands for volume unit, and we can see that there's some positive range there. And on the left, we see a dBU meter, okay? And you can tell, again, here we've got some positive range, okay? So the first thing to know about analog meters is you could have some positive range. And the second thing to know is that the 0 point is the optimal point that you might want to record at. And this is the best compromise between distortion when you run it too hot and the noise floor when you're running it too quietly. Okay, so when you're dealing with these analog scales, you need to note that by default they're usually averaged over a specific time window, i.e. they're not showing their peak levels. And this is important because you weren't so bothered about absolute clipping because they tended to soft clip, but you were really, really interested in avoiding the noise floor in the low levels. But that's different to our bog standard dBFS digital levels, because they're not only a reference of 0 being the maximum permitted level, but also by default their peak. So you can't really compare the two very easily. So when you're looking at the metering, you've got to make sure that you're knowing whether it's a digital meter and whether it's a peak or an average meter, and adjust how you use them based on that information. And another important thing to note is just because you're finding a particular meter on a digital audio workstation doesn't necessarily mean that it's a digital peak meter. And often you even have models of old school analog equipment that will use the original meter type of that unit. So just because you find it in your digital audio workstation doesn't necessarily mean that it's a digital meter. So we've explored the dBFS scale and know that that's the most primitive form of peak measurement inside your digital audio workstation. But what is the most primitive form of average measurement? That is called dBFS RMS. And as the name suggests, it's still using the same decibel and full scale range. So 0 is still the maximum permitted value, and all of your values below that are going to be negative. But this time it's averaging that out over a period of time. So if you were to just average the raw data, it would be misleading, because audio signals tend to oscillate between periods of positive and negative pressure. So if you had a sound that is particularly pure, like a sine wave, this would leave average values close to 0 because the positive periods would cancel with the negative periods. Obviously, this is something that we don't want, and this is not how we're hearing anyway. So to avoid this, people use root mean squared measurements. So what this does is it first takes each sample and squares its value. So this naturally will turn any negative numbers into positive numbers, however, their values will be higher. And then the next step is to take an average of that, okay, take the mean of it. And then the next step is to take the square root of it, which will bring the signal strength back down to a reasonable value again. So this whole process is just to avoid the problematic nature of oscillating between positive and negative pressures. Okay, so let's go ahead and go back into Pro Tools and look at how you might see RMS values. Okay, so we're going to go back to this audio track, and instead of being on Pro Tools Classic, we're going to go to RMS. So we can see here that 0 is still our maximum value, and we're going to be in negatives from there. But just look at how high this bar graph is this time.
Cross the lips and your fingertips. Do what it takes to get you off your kicks. You maybe better not stick with it. I lost my faith in a darker pit. Settle for one, or I settle for two. I lost my way and I lost you too. You play my head and you mess my mind. I bear a treasure for you to find, 'cause I'm a liar.
Okay, so what you saw there is that when we were on the RMS scale, our level was round about -15. But when we're on the dBFS peak scale, we could see that we were peaking around -3. So RMS values typically tend to be a lot lower than the peak values, which makes sense, is that the average loudness is going to be lower than the peak loudness. Okay, and I want to train you to see this in various different ways. So another way that you are often likely to see peak versus RMS levels is actually simultaneously. So when I play this, you're going to see two readings. You're going to see a higher bar, which will be kind of striped, okay, and a lower solid bar, which is going to be the RMS level. So you've got the higher striped peak and the lower solid RMS.
Cross the lips and your fingertips. Do what it takes to get you off your kicks. You made your bed and I stick with it. I lost my faith in a darkened pit. Settle for one, or I settle for two. I lost my way and I lost you too. You play my head and you mess my mind. I buried treasure for you to find. 'Cause I'm a liar, but I'm a loser.
So why would you want to look at a peak meter versus an RMS meter? Well, you would look at the peak meter to make sure you're not unintentionally clipping your audio and that you're not distorting it. But our ears aren't necessarily hearing those fast fluctuations. So an RMS average measurement is closer to actually how we're hearing the audio. However, it's not a perfect system. So to look at some of its shortfalls, let's go back to our slideshow. The problem with RMS measurements is that our ears are not equally sensitive at all frequencies. This means that two different sounds could read the same RMS value but would be perceived as a different loudness by our ears. Okay, and this was shown by the equal loudness contours or Fletcher-Munson curves. So over the years there's been several studies of our perception of loudness. And these started with the Fletcher-Munson curves, which are shown in blue in this diagram here. And over the years they got updated and are now known as the equal loudness contours. So these are the readings in red. And what effectively this diagram shows is that our ears are most sensitive to high frequencies, but much less sensitive to low frequencies. And this means that it takes way more energy at low frequencies to be perceived as the same loudness as a higher frequency does. Okay, and what this is showing on the diagram is the curve of our ears at various different volume levels. So at the threshold of our hearing, i.e. the quietest sound that we can comprehend, we can see that we're most sensitive to sounds between kind of 1K and 6K, which makes sense because that's the kind of intelligibility of human speech. Whereas at lower frequencies, it takes way more energy for that tone to be perceived as the same volume. Okay, so that's what these curves are showing. And how they did these tests was give people a test tone, typically at 1K as a reference, and then asked the test subject to identify when other tones were the same volume as that test tone, and that's how they worked out these curves. So this is showing not only is our hearing most sensitive in that kind of high frequency range, but it's also showing that as sounds get louder, that it flattens off more. Great. So how would you go about making RMS measurements even closer to how we perceived sound? So the way that people are currently doing this is called K-weighting, and this is to literally take the audio signal and filter it, i.e. EQ it, before an RMS reading is taken. And how they filter this is basically as a rough approximation of the opposite of our human auditory system. So it takes way more low information for it to be perceived the same volume. So by removing low frequency information and increasing high frequency information, that can represent close to what our ears are hearing. Okay, so for instance, if your audio signal doesn't contain a lot of low frequency information, okay, it's going to appear even lower once it's gone through this filter, and therefore the RMS reading is going to change weighted by frequency. Okay, and this has been utilized in several different types of digital meter. So the first is LKFS, and this was invented by the International Telecommunications Union, and that stands for Loudness K-Weighted Full Scale. So again, this is decibels, full scale, but it's weighted by this K-weighting. And this was identified in their BS 1770 standard. But then the European Broadcasting Union built on this and added several updates. And this included a gating system to stop long passages of silence or low-level information from skewing the readings too much. And this unit was defined as LUFS, or Loudness Units Full Scale. And this was defined in their standard, the EBU R128. Now, at this point, the two scales are different because one has this kind of gating and other improvements, and the original LKFS doesn't have any of that. However, in 2011, the ITU also adopted these changes made by the EBU, and since then, the LKFS and LUFS are functionally identical. So whilst the two scales were different in their origin, since 2011, they're identical, so you can use either one. I tend to prefer to use LUFS because that's the one that tends to be used on more of the loudness meters that I tend to encounter, but either is fine. Now, one more thing to mention about LUFS readings is that they also give you several types of readings. It's not just one RMS level anymore, you're getting several LUFS readings. And this is because the R128 guidelines were also designed to help broadcasters set some specific targets to make sure that the advertisements weren't louder than the station's core programming. And because the EBU is a broadcast union, this was a kind of important topic for people. Okay, and so the three different kind of timing references that they give is a momentary measurement, which is 400 milliseconds averaging. Okay, you get the short term, which is averaging over 1 to 2 seconds, and you also get long term or integrated loudness. So this is the loudness over the whole period that the piece is playing. And this is the one that you typically use when you're producing music, and generally you're going to be visually only, and it's not attached to some sort of visual, or it's not some sort of sound effect. Okay, but the momentary and short term are really, really important when you're doing broadcast, because you have some level of disparity between like momentaneous things like, say, a gunshot in a TV show compared to the dialogue or the kind of background music. And this kind of helps to keep programs following roughly the same specs, so therefore one program isn't going to be dramatically louder to another. Okay. In this video, we're just going to be mainly covering the musical uses of this. So let's go back into Pro Tools, and I'm going to show you that RMS measurements are not equal to LUFS measurements by using a sine wave. So I'm going to play this briefly. So that's a low frequency sine wave there at 80 Hertz. And so if I bring up Isotopes Insight open here, and what we can see here is we can see our three LUFS readings, the integrated level over the whole piece, the short term, and the max momentary. Okay, we're also seeing over on this left hand side, we're seeing the peak level on this top reading and the RMS level here. Because this is a static test tone, the RMS and the peak are actually the same. Okay, but notice that this dBFS and dBFS RMS measurement are not the same as the integrated measurement. So let's just refresh this. And we can see that an 80 Hertz sine wave at -20, here -20, actually gives an integrated level of -25.5 LUFS. So it's actually lower than the core low frequency. But if we take the signal generator and let's move this up to 1K. So now we're at 1K, and let's bring up Insight again and let's refresh this. Notice now we're at -23, okay? But the peak and the RMS there are both at -20. So we can see that we're reading 2 decibels higher in LUFS at 1K than we were at 80 Hertz. So the two are not identical. However, that being said, a couple of dBs here and there across our whole range means that if you've got a high RMS level, you're likely to also have a high RMS level. The disparity between them isn't going to really skew things too much. Okay, so let's just go ahead and let's put this on the track again, and I just want to show you how these levels change as a track is playing. So what you should see is the max momentary kind of reaches its peak level quite quick. The short term is next, but then the integrated level is actually going to change more slowly and react over a longer period of time. So let's refresh that, okay? And these will be reflected in these two bar graphs here. So we've got the integrated level, and this shouldn't move too much, especially once it's taken a bit of time to find the integrated level. It's going to stay fairly static. And then the short term is going to bounce a little bit, but the momentary, you're likely to see way more movement. So let's just have a listen.
Cross the lips and your fingertips. Do what it takes to get you off your kicks. You made your bed and I stick with it. I lost my faith in a darkened pit. Settle for one, oh, I settle for two. I lost my way and I lost you too. You play my head and you mess my mind. I buried treasure for you to find. 'Cause I'm a liar, but I'm a loser. But baby, you know I'm a joker too. But the joke's on you. 'Cause I'm a liar, and I'm a loser. But baby, you know I'm a joker too. But the joke's on you. Speak your riddles, you're mad.
Okay, so what you could see there is that our three levels were changing quite a bit. Okay, so one thing that's useful when we're dealing with music is that the integrated level is calculated on streaming platforms across the whole track from start to finish. So when it's getting volume normalized, it's doing that calculation based on the whole track, not its short-term or momentary loudness. So when we're dealing with music, this is the key one, the integrated. Okay, but another good metric for working out how dynamic your music is actually this loudness range here. And this is kind of telling you the difference between the kind of momentary loudness and its long-term loudness. So we could see while that was playing that you had kind of 2.4 decibels LU of disparity between the loud bits and the quiet bits. So the larger this number is, the bigger the disparity and the more dynamic your music is, and the smaller the number, the more flat and the more dynamically controlled it is. Now, it's not for me to tell you what's a good or bad value, it's kind of really genre specific. However, at the same time, you should err on the side of caution and try and not make this number too small. So the final type of metering that's important to understand in the digital domain are called true peak meters. So let's go back to our slideshow. So when you have extremely limited compressed or clipped audio that's very, very close to 0 dBFS, you might find that when the signal is turned from a digital discrete version back into an analog continuous signal, sometimes you can end up with some clipping occurring. And these are called intersample peaks and can cause an audible distortion. So if we look at this diagram here, we can see that the red line indicates the maximum level, 0 dBFS. And we can see that all of the samples, which are the black circles, aren't actually exceeding that level. However, when the digital to analog converter makes that back into an analog signal, it's basically what's called interpolating it, which means it's trying to make the smoothest representation between each of these samples. And what this means is that this level actually exceeds the maximum level, and this can basically create distortion. Okay, and this is something that a lot of meters are not showing. So people invented true peak meters that show you the level of it post this conversion. Okay, and we can see this in many modern meters. So let's go back to Pro Tools and I'm going to show you this. So here we've got a meter that not only shows you the LUFS readings that we saw before, okay, but we can go into true peak mode here and take a look out for this value TP max. So this is going to be showing you the maximum peak, not just at the point of samples, but between that, as if it had been converted back to analog again.
Cross the lips and your fingertips. Do what it takes to get you off your kicks. You made your bed and I stick with it. I lost my faith in a darkened pit. Settle for one, oh, I settle for two. I lost my way and I lost you
Okay, so notice there that because this had some headroom to 0, that even as a true peak, it's not actually clipping. But what happens when we load up a limiter and we brick wall limit it so that the out ceiling is minus 0.1? Okay, and what we're going to see now when we play this is that we're actually going to end up with some intersample peaks.
Cross the lips and your fingertips. Do what it takes to get you off your kicks. You made your bed and I stick with it. I lost my faith in a darkened pit. Settle for one, oh I settle for two. I lost my way and I lost you too. You play my head and you mess my mind. I bury treasure for you to find. 'Cause I'm a liar, but I'm a loser. But baby, you know I'm a joker too. But the joke's on you. 'Cause I'm a liar, and I'm a loser. But baby, you know I'm a joker too.
Okay, so notice there that we've got some peaks that are going over 0. And to kind of alleviate this, we could do several things. We could bring the out ceiling down so that you've got a bit more headroom, or you can turn on true peak limiting. So this is setting the out ceiling such that even between samples it can't peak. So now let's reset that and let's have a look at what it's reading.
Cross the lips and your fingertips. Do what it takes to get you off your kicks. You made your bed and I stick with it. I lost my faith in a darkened pit. Settle for one, oh I settle for two. I lost my way and I lost you too.
So notice there that now we've turned on true peak, it's actually not going above minus 0.1. However, there is a caveat to this, and this is that when you convert this to a lower kind of quality audio file, so an MP3 or AAC or whatever, typically you can still end up with intersample peaks during that creation process. So one thing that I like to do is I like to turn on this codec and preview what it would be like as a 128 kilobyte MP3 or AAC. Okay, and notice now when I play this, we might start to get some peaks.
Cross the lips and your fingertips. Do what it takes to get you off your kicks. You made your bed and I stick with it. I lost my faith in a darkened pit. Settle for one, oh I settle for two. I lost.
So during that creation process, it's actually ending up clipping again. So one way to get around this is that people recommend that for streaming platforms you have an out ceiling of -1. So let's just reset that and let's see what it comes at now.
Cross the lips and your fingertips. Do what it takes to get you off your kicks. You made your bed and I stick with it. I lost my faith in a darkened pit. Settle for one, oh I settle for two. I lost my way and I lost you too. You play my head and you mess my mind. I bury treasure for you to find. 'Cause I'm a liar, but I'm a loser. But baby, you know I'm a joker too. But the joke's on you.
Okay, so we had less of them, but they were still there. And at this point, I might decide to kind of bring the threshold up a bit so it's not doing quite so much.
Cross the lips and your fingertips. Do what it takes to get you off your kicks. You made your bed and I stick with it. I lost my faith in a darkened pit. Settle for one, oh I settle.
Okay, so we're no longer clipping. But it's important at this point to kind of stress that sometimes intersample peaks aren't a big issue, and it should really be your ears that decides this, but you use these visualizing tools along with your ears to decide whether it's a problem or not. I usually find that if something is extremely loud and distorted anyway, those intersample peaks tend to kind of be more audible and more detrimental to the sound. However, again, just let your ears decide. So I hope you enjoyed this video, and I'm hoping that you're getting to grips with the different types of meters and where you might want to use them. If you've got any questions, please leave them in the comments below, and I hope to see you again soon.